Hello. So my name is Zeshan Ali, and I was working in this project as a postdoc for 3 years. And this is the last subject on which I have done research. So today I will present gesture recognition using chipless RFID tag held in hand. So the outline of this presentation is first I will present motivation, then principle of operation of the technique, and then some measurements and gesture recognitions. Then we have some video demonstrations, and then I will conclude my talk. So hand gesture recognition is have enormous applications in IoT. Mostly it is used these days in gaming, but these can be used as a sign language, virtual manipulation, daily assistance, palm verification, and human-robot interaction. So we have quite a few number of devices which do hand gesture recognition these days. One of them is Oculus Quest from Meta, that was previously Facebook. And they have these 4 optical sensors to decode the hand gestures. And normally all the gaming devices are based on visual sensors. But actually there is a big problem with the visual sensors, because if the hands are hidden or it is behind some object, this technique cannot work. And also if there is a bad light condition, so we need a maybe IR sensor to make it work. So for this reason, we are going to present the hand gesture recognition using chipless RFID. The principle of operation of this technique is that if we have a chipless RFID tag in front of antenna at a d0 distance, and we take a measurement, and then we move it into the 3D plane, and we do another measurement. So from the phase difference of the measurements, we can calculate the delta D, the change in the distance from antenna to tag. And we will exploit this delta D to localize the tag in 3D plane. So to do that, we realize a special chipless RFID tag, which has a arrangement of the scatters in a check pattern to make the multilateration possible. So the chipless RFID tag is based on 45 shifted dipole, and it's a depolarizing chipless RFID tag, which is quite well known in chipless RFID now. The overall size of the tag is 9 times 9 centimeters square, and the frequency of working is from 3 to 6 gigahertz. Classically, the multilateration to find to localize the target, the classical multilateration is based on one target and multiple antennas. But in our technique, the multilateration is inverted. So we have one antenna and multiple scatterers. So to know that the position of the tag, we have to solve the system of equations based on 8 equations, where x, y, z is objective, x, s1, and with the subscript s is the position of the scatterers on the tag, and the position arguments with the subscript a is the position of the antenna. Ideally, by solving this equation, we can find x, y, and z, but we have some problem here because of the phase pattern of we have now 2 phase patterns of antenna targets, one from antenna and one from the tag. And the problem is that we are also in not in the far field. The phase is not circular, so there is some perturbation. So, but if we combine these 2 phase patterns, we do not have circular phase patterns. So we are using a candidate search, which is optimization by using the minimization of squared error, where DI is equal to D, and GCI is the candidate solution. So we actually try to find the X, Y, and Z over the whole 3D volume by adding the Gaussian randomness in the candidate, and it's quite really fast. So this is the overall algorithm for 3D localization. So first we have acquisition of the signal, then we do a while loop for each scatterer from 1 to 5. We have continuously acquisition of the signals, and we see that for each displacement, if there is a phase change, phase wrapping, we unwrap it, and then we use equation that we first calculate delta T, then we do utilization, and then we do minimize the mean squared error to find the actual X, Y, and Z. So for the measurement setups, we have two measurement setup. One is the 3D positioning table, which is realized in-house. We use the equipment for 3D printer to, actually it is the equipment of 3D printer. Actually, the slides, motorized slides, are exactly as we use in 3D printer, and we use it for 3D positioning table. 3D controller is the same as 3D printer. And this is quite accurate setup. It has an error of positioning of few millimeters. This is done because we would like to know how much there is error in 3D positioning, because as I explained, because of phase perturbations, we do not have exact 3D localization. But even if we do not have exact 3D localization, we need estimate pattern to detect the gesture. The second measurement setup is we are using human hand. We are holding the tag in the human hand, and we are doing the gestures in front of the antenna. So we have, in this study, we have 6 ideal gesture trajectories, X, Y, Z lines, and 3 circles, that is X, Y circle, Y, Z circle, and X, Z circle. And these 6 gestures are done first by the 3D positioning table and then by human hand. Okay, after calculating the measured trajectory by using 3D localization, we use convex hull to make the gestures in an enclosed form. And then we use a very fast similarity metric that is called turning distance. It's a kind of a metric which try to minimize the distance between turning distances by minimizing theta and t. So for this reason, it is independent of rotation and scaling. So even our shape is rotated or it is scaled, the result will not be affected. So if we have this convex shape of our measurement, and if I compare it with ideal circle, the turning distance will be close to 0. So by this way, we are trying to find the gestures. Here we have some measurements by using 3D table. So it's continuous 50 measurements of each hand gesture trajectory. The setup is quite accurate, so that's why we do not see anything here, but these are 50 overlap X line, Y line, Z line, XY circle, YZ circle, and XZ circle. And we have presented here the detection in terms of the confusion matrix. Here the columns are actual gesture and the rows are estimated gesture. And each cell is showing the detection statistics and the number of gestures that we have detected correctly. So for most of the gestures, we have accuracy of 100%, but for Y line and XZ circle, we have 4 gestures that are misclassified. This is because the algorithm is very fast, and sometimes the full trajectory is not taken into account in the comparison. For example, in Z line, because of the phase distribution, there is a small tilt. And if I calculate sometimes the next cell, it can represent a circle. So that's why it is detected as a circle 4 times. So but this is not very common. So here we have some other measurements. We are doing some measurements of X, Y circles using at different height from antenna to tag. So at the nominal height, the detection is quite good. That is that one is equals to 10 centimeters. And at Z2 equals to 15 centimeters, the radius is enlarged. This is because of the phase perturbation that I have already discussed. This problem exists actually in this case. And then we have Z3 at 20 centimeters and Z4 at 30 centimeters. The results are not encouraging at 30 centimeters because these tags are not designed to be read at larger distances. The nominal range of Chipless RFID tag reading for these kind of scatterers, the shorted 45 dipoles, is 20 to 25 centimeters. So that's why we don't have accurate results on 30 centimeters. In terms of detection, up to Z equals to 20 centimeters, the detection is 100%, and at Z equals to 30 centimeters, we have only 70% of the accuracy, but overall accuracy is 92.5%, which is quite okay. Let me explain just this confusion matrix. This is a modified confusion matrix, which is the circles are here, and all the misclassifications are added in other class. So it's X line, Y line, Z line, XZ circle, YZ circle, to make the confusion matrix in a compact form. Then we have some other measurements. We measured 50 trajectories for each radius, starting from 2 centimeters up to 5 centimeters. For R is equal to 2 centimeters and 3 centimeters, the trajectory is quite circular. But as we go further, there is some perturbation in the localization, and it's surely due to the phase problem. In terms of detection, we have some up to for 2 centimeters and 3 centimeters, we have 100% of accuracy, but at R is equal to 4 centimeters, only one trajectory was misclassified, and for 5 centimeters, 39 misclassifications we have found, and only 11 was correctly detected. So from this up to this, we are okay that we are sure that the technique can work into 10 times 10 times 10 cubical volume. So if the gesture is confined into a volume of 10 times 10 times 10 centimeter cube, this technique works. But if we go further than that, some anomalies can happen. And here we have some video demonstration. So this is the measurement setup. Yes, here a table was cut, and the equipment of 3D printer was installed to make this setup. This is the arm of styrofoam to place the tag, which is at microwave, which is invisible, and it is controlled by the controller of 3D printer. it's a short form of the demonstration, but real demonstration is very long for all the gestures. This is for Z line, and the line is quite straight, and gesture is detected. And then we are moving very slowly towards Y, because if I will move very fast, the Y gesture will be detected. So that's why we are moving very slowly to make a circle. It's quite on the plane, so there is no disturbance from the Z. Then the second part of this presentation is measurements using human hand. So now I was holding the chipless RFID tag in hand and doing the measurements. And here we have presented the 6 measured trajectories for 6 gestures: X, Y, Z, and Z line, and X, Y, Y, Z, and X, Z circle. Similarly, we have done also statistics of gestures when I was holding the tag in hand, Z line and XY line, and we have found that only one gesture was misclassified. But this is dependent purely on the human hand, how the subject is accurate or not. If somebody will be not accurate, the statistics will be not accurate. The overall accuracy we have found here is 95%. It's quite random. Sometimes I had 2, misclassification 3, but we have presented here the best results. Then this is the final slide. Because of the RF, this technique can also work if the antenna is not visible to the chipless RFID tag. We have 3 types of objects. One is wooden board. The second is gypsum board, which is normally used in France in the wall. So this technique can also work behind the wall. And the second is chipboard, which is quite a thick chipboard used in the tables. And we have done 2. We have measured 2 hand gesture trajectories, Z line and XY circle. And in all these 3 cases, the trajectory was detected accurately. So this means that this technique can also work hidden in a furniture, behind the wall, or under a desk. So this is a demonstration. First is X line. This is Y line. This is for Z line. This gesture is for XY circle. Now I think YZ circle, XZ circle. And this is for YZ circle. To conclude this presentation, this technique that we have presented is a model-based technique. It doesn't require any kind of learning or deep learning or complex models. It's really purely 3 equation-based technique. We can implement it in real time. and it can work in 10 times 10 times 10 cubic centimeters volume. And also it has capability to work under the objects. The other possible features are it includes all chipless RFID functionalities like identification, authentication, whatever we want. We can even authenticate the person who would like to interact with the system, that is if he has a specific kind of tag or not. And it can behave like a computer mouse, but this is quite really far. I have added. So I would like to thank you, ERC, for funding this project and allowing me to work in this project. If you have any questions.
One question. Yes.
Thank you for the interesting presentation. I was wondering, you showed like linear motion and circular motion. Did you also make a localization of the angle, PTO, and stuff like this?
Angular, we were trying to implement. There is already one research done by Nicola for Angular sensitivity of the tag, and I was trying to integrate this Angular sensing in this technique, so that we can make a click. So I was thinking that, okay, this is a mouse, and then we can, by a rotation, we can make a click. Actually, the problem is that if the click is large, if the angle disturbance is very larger, like up more than 5 degrees, we lose the localization. But if we are very precise in the angle movements, we can surely. This system is not affected, but we can integrate the angle sensitivity in that.
Like one antenna, you are like three different antennas.
Yes. Yes, an antenna array can be a good solution for that. But these kind of antennas, they are really directive. But we need an antenna array, which is a kind of a separate work to make, and we have also to estimate its phase pattern, that how it's behaving. Because if we have 4 patterns, it will be very difficult to have circular pattern with the 4. So it's a different kind of research. Maybe somebody will do next.